Hello everyone, today we're going to cover transient conduction in heat transfer. This is chapter 5 of our textbook. So what we considered so far, what we talked so far is mostly a steady state condition, right? The boundary conditions on the boundaries, on the walls, we usually use an example, is consistent, is fixed. For example, if we assume the wall behind us in the classroom, that in one side facing the air outside, on other side facing the air inside the room, then for a short limited time, we can assume the temperature on each side is fairly constant. So this is a steady state. The temperature or the condition on the boundary doesn't change with time for a limited time. Now let's consider if we have a transient case where we can assume temperature on the boundary is a function of time. It's not anymore assumed constant. For example, if we use temperature on the same wall for a period of 1 day, then because the temperature perhaps in the morning, in the noon, in afternoon, at night are different, then temperature on the side, on the wall is changing by time, so we call it transient. That's the topic of discussion today. So there are different methods to solve transient conduction problem. One is using partial differential equation. That's another topic of discussion today or even in this course. Basically, over there we're using heat equation to solve the problem, to solve the transient problem. Another method to solve such a transient conduction is using an approach called lumped capacitance method. That's what we're gonna cover today. So this is, we're gonna talk about in chapter 5 only. There are other approaches as well, such as approximate method. We're not covering those. And of course, numerical method. Numerical method, that's basically with some simplification, try to solve the governing equation, and it's a fairly simple approach to solve any heat transfer problem with a good accuracy. But this is the discussion today, lumped capacitance method. Let's see. Let me add more slide. Looks like I started. Nice. Now, to define the lumped capacitance method, consider, so today we're going to talk about lumped capacitance method. And let me shift this all the way up. Consider an infinite plate. Initially at temperature Ti, T sub I means initial temperature, and suddenly the walls are put at another temperature which is T1, T sub 1. So initially it was at T sub I, and starting at time 0 onward, we're going to push it to T1. Now the question is, what is the spatial temperature distribution? What is the spatial temperature distribution as a function of time? As a function of time. And the spatial means based on location, basically. So we have a wall that initially is at temperature T sub I. So this is x direction. Let's assume the thickness of this wall is 2L. So 2L is the thickness of the wall. So starting the time for time greater than 0, the initial temperature changed to T1. So those sides are going to T1, T1. And again, the inside of the wall was initially at T sub I, suddenly changes to T1. Now, how we can solve this? If you remember the main governing equation for conduction, let's go write it down. So we had second derivative of temperature with respect to x plus del 2t del y squared plus del 2t del z squared plus, if we have any heat generation, then this is a heat generation term, q dot over k is equal to rho, which is density, C sub P specific heat capacity divided by thermal conductivity del T over del time. So that's the main governing equation we have. Now, for this case, first of all, we're assuming any heat conduction happens only in one direction. So let's go ahead and assume there's no heat transfer along the Y or no heat transfer along the Z direction. So these two terms go to 0. These two terms go to 0. We have no heat generation, right? There's no heat source inside. So the heat generation term also goes 0. We're gonna keep this time the right-hand side term because we have a temperature changes versus time. So it's a transient problem. So we're going to keep the right-hand side and we're going to keep the left-hand side, right? So if I go ahead, write down the simplified form, I have second derivative of temperature with respect to x should be equal to rho Cp over k del T over del lowercase t. Now, if you remember, we defined thermal diffusivity before. So we called it alpha thermal diffusivity. And the unit was meter square per second. And alpha was defined as K over rho Cp. K is thermal conductivity of the material, rho is the density, and Cp is the specific heat capacity. So we can use the alpha in this term, which is the reverse of alpha. So our governing equation in simple form would be second derivative of temperature with respect to x equal to 1 over alpha instead of rho Cp over K del T over del T. So this is going to be the main governing equation or solving transient conduction problem. Now, our goal is to solve this governing equation. This is a second derivative, partial differential equation, so function of x and time, and it's a second derivative. Now let's go to the long capacitor method and how we're going to solve this governing equation. So we're still talking about lumped capacitance method. Now assume that there are no temperature gradients. There are no temperature gradients in an object as it changes temperature. Okay. As it changes temperature under external heating or cooling. This is supposed to be cooling. So what we're saying is that let's assume we have a bucket of water or any liquid really. This example, let's assume we have a bucket of water, liquid, and liquid is initially at T infinity. Okay, let's move on. And we have an object. You can assume a metal, small object. And this object is initially at T sub I. And let's assume Ti is much, much bigger than T infinity. Yes, so Ti is much larger than T infinity. One example is that imagine you have a metal from a stainless steel, really hot, coming out of the oven, so you can hold it with the gloves, and you put it in the water at the room temperature. So the temperature difference is large. And we are expecting as soon as we put the metal piece into the water, the temperature of the metal goes down, correct? And after a while, perhaps it reaches the temperature of the water. So this is an example we're gonna do. So we're gonna, at time equal 0 and onward, we're gonna time greater than 0, greater equal to 0, we're gonna drop this hot metal at the temperature of Ti into this cold liquid. So we're gonna have this inside, and we're gonna monitor the temperature change inside the block, which was initially at Ti and then going to be at temperature T, and T is a function of time. So depending on what time, that T can be different. So T is a function of time, so I show it as T of function of temperature, lowercase t. Now, if I'm gonna go ahead and solve this problem, what I'm gonna do, I'm gonna take this hot metal piece and show a control volume around it, a control surface in a 2D study. So let's assume this is my control surface if we're studying a 2D. So control surface. Now I can go ahead and write energy balance across the control surface. And energy balance, remember from the steady-state conduction, we usually say amount of energy into the system plus amount of rate of energy generated inside the system should be equal to energy going out plus energy stored, right? So this is a simple form of energy balance. In our case, if you're assuming the metal piece in the water as our control surface, then no energy comes into the metal piece. We don't have energy generated, so these two terms go to zero. We have some form of energy going out, which is convection, which is the amount of heat we put into the liquid, into the water. And then there's a change in the internal energy of the object, change in the temperature of the metal bar, so we have changes in energy stored. So basically, I can reduce this form saying that energy, so by the way, you can call all of them rate, so rate of energy. So energy by the amount of energy stored should be equal to minus of amount of energy going out, correct? Because this side becomes zero, so you can pull the energy out, rate of energy out to the other side, so this is what you get. And as mentioned, amount of energy going out is amount of energy we put into the liquid, which is in the form of convection. So energy out, you can write it as minus comes down, you can write it as H, the transfer coefficient inside the liquid, A, the surface area between the liquid and the object. Later we call it AS, right? Let's go ahead and call it now surface area, A sub S. And temperature difference between the temperature of the object, T, minus temperature of the liquid, T infinity. Temperature of the liquid. On the stored rate of energy, we have rho density, V volume of the object, Cp specific heat capacity of the object, and dt over d time. Variation of change inside the object as time, as a function of time. By the way, rho times V gives us mass, right, M. So this is, left-hand side is nothing but M Cp dt over d time. dt over d time is defined as change in temperature per unit time. Okay. Now, to solve this, what I'm going to do, I'm going to define a theta as what we did in the past. So I'm going to go ahead, define a new temperature variable, theta equal to temperature of the object at any time, T minus T infinity. So we also discussed it in class a few sessions ago that if theta is defined T minus T infinity, which T infinity is constant, that's a fixed temperature of the liquid, then derivative of theta with respect to time is going to be dt over d time minus d t infinity over d time. Makes sense? And we know that t infinity is constant, so derivative of that with respect to time is 0. So that leads to having d theta over d time is equal to dt over d time. So you can go ahead, use the new variable theta, and whenever you have dt over d time, you can just replace it with d theta over d time. So if I go back, one slide back, and use this final form of equation I had for t minus t infinity, I'm going to put theta, and for dt over d time, I'm going to put d theta over d time, and this is going to be my simplified version. So I would have rho v cp, instead of dt over d time, I want to have d theta over d time equal to minus h surface area. Instead of t minus t infinity, I'm going to have theta. Now, in order to solve this, I'm going to separate variables, theta and time, and then integrate it. So what I'm going to do, I'm going to have rho v cp, keep it on the left hand side, bring the h and ac on the left as well, h and as, sorry, surface area, and keep d theta, and since we're separating the variables, so theta will be to the right left hand side, and on the right hand side all remains is dt, which we're going to push it on the right hand side. And don't forget we have a negative sign here as well. So this way I separated the variable theta from time, from t. Now I'm going to go ahead, integral both sides. Again, rho vc over has, all of them are constant, so they can come outside of integral. And on this side I have integral for dt. Initial temperature was Ti, so with my new variable it's become theta I. So remember, theta is T minus T infinity, so Ti means theta I, which is Ti minus T infinity, right? And for any temperature, you can simply call it theta with the new variable. And for time, it varies from starting time all the way to the end, which we call it just t. Now, if I go ahead, integrate both sides, I have rho v cp over has as a constant, remain as is, integral of d theta over theta, or integral of dx over x is natural log of the variable, in this case theta, changing from theta I to theta, equal to integral of dt, I guess I'm pushing the button, sorry, would be simply minus t from 0 to t, which becomes minus t again. Now, ln theta minus ln theta sub I, you can call it ln theta divided by theta I. So I can explain. So again, ln theta minus ln theta I, you can show it also in this form. And on the right hand side, I have minus t. And also, I'm going to bring these constant to the other side, which becomes h AS over rho V CP. Almost there. Now, in the next slide, I'm going to show that natural log of theta over theta I, this is theta I, equal to minus t times a constant inside the parenthesis. You can also show it in this form, that theta over theta I is equal to e to the power of, or exponential function of, minus h as over rho vc cp times t. That's the very final form we're going to use in this chapter. So I can go ahead, even define theta and theta I as well, and we know that theta is t minus t infinity. Theta I is Ti, the initial temperature, minus T infinity, right? That's the left-hand side equal to exponential function, or e to the power of, I have minus a constant, because h is constant, a is constant, density is constant, volume is constant, Cp is constant, times time. So this is the final form we're going to use today in this chapter, and everyone really should be comfortable using that. So by having this, let me use a highlighter. Can I change the color? Yes. So if I know the initial temperature of the object, if I know the temperature of the liquid, which is T infinity, right? If I know the heat transfer coefficient inside the liquid, if I know the surface area of the object, the area around the object, if I know the density of the object, volume of the object, Cp of the object, I can find out what is the temperature of the object at any time. This way, I should be able to plot the spatial temperature distribution versus time. So if this is temperature, if this is time, as soon as I drop that hot object into the liquid, initially it's at Ti, which is really hot, and minimum temperature, which is the temperature of liquid, is T infinity, right? So you can say, okay, by having this equation, by substituting time, 10 seconds, 20 seconds, 30 seconds, 1 hour, whatever, in seconds, of course, the temperature you want, you can find the temperature at any time, and you can go ahead and plot it, the temperature distribution of the object, using this equation, temperature distribution. So this is the main equation. You don't need to remember this, but it always helps to understand it very well, even remember it, it doesn't hurt. And so in an exam, it should be given to you. It's an open note form. So by knowing temperature, infinity Ti, and other parameters, we can find at any time what is the temperature of the object. Now, let's go one step further, define another new variable, we call it time constants, or we call it thermal time constant. So let me go ahead. So let's talk about thermal time constant, which we showed with tau. So thermal time constant is defined as rho Vc Cp divided by HAS. the reverse of what we have in this equation. So if I use the tau in long capacitance equation, the star equation, I can show it as t minus t infinity divided by ti minus t infinity equal to e to the power of minus t over tau. So the whole thing here, HAC over rho VCP, we can call it 1 over tau. So this can be another form of this equation. Same thing, we're just using a new temperature variable, time variable. Sorry. Now let's go define a new number. So far we worked with a Reynolds number, perhaps, in mostly fluid mechanics and convection we're going to cover. Here, let's talk about, still we are in lumped capacitance method. Rewrite the capacitance. And let's talk about bio number. So bio number, which we showed as BI, is defined as H, heat transfer coefficient, LC, a characteristic length, divided by thermal conductivity, K. So in this definition, L sub C is characteristic length. We're going to talk about it more later. And LC is defined as volume divided by surface area. So volume of the object divided by surface area of the object gives us the L sub C. H is heat transfer coefficient. And K is thermal conductivity. Now let's consider this wall again. That was initially at Ti and then suddenly starting at T equals 0 and onward it becomes T1, remember? Let's assume in another form that this is the wall. On the right hand side, you have a fluid moving. So basically you have convection going on at temperature of T infinity and heat transfer coefficient of H. There's a movement of the fluid on the right hand side. Let's call the temperature on the left wall as TS1, surface temperature 1. By the way, this is where X stopped. So this is X equals 0. And the thickness of this wall is L. Now, in this section, in this slide, we're going to talk about when we can use long capacitance method. Or can we use long capacitance method for any transient conduction? The answer is no. There are certain problems that if a bio number is less than 0.1, we're going to talk about more now, then we can go ahead and say, hence, because the bio number is less than 0.1, we can go ahead and use the long capacitance method. we can go ahead and use the previous equation we developed here. If bio number is greater than 0.1, then we cannot use this method accurately. So we have to use other methods that we're not gonna really cover much in this course. So this approach is only working if the bio number is less than 0.1. And we're gonna talk about why this is happening. Now, if I go rewrite the bio number we said bio is defined as H LC over K, correct? What I'm gonna do, I'm gonna write same bio number in this form. On numerator, I'm gonna have LC over KA, and denominator, I would like to put 1 over HA. So this C should be lower, small sum. So, is this familiar? The numerator is LC over KA. The denominator is 1 over HA. What is this? What is this? Anyone can guess? So from what we covered in chapter 2 and 3, I believe, we're calling the LC over KA as thermal resistance by conduction, remember? So LC is the thickness, in this case, of the wall. Ka is the thermal conductivity and surface area. So that shows the amount of resistance inside the wall by conduction. 1 over HA, we talked about it, that was thermal resistance by convection. Or in other words, bio number is comparing the resistance by conduction inside the solid material versus resistance by convection outside of it, correct? So if bio number is small, what that means? So very small bio number means the resistance by conduction is very smaller than resistance by convection. Correct? When this happens, for example, if you have a spherical copper, which because the K, the thermal conductivity inside the copper is so high, the resistance by conduction is really low compared to a wooden object where K is low, plastic object where K is low. So, and on the other side where resistance by convection is high, when basically when I have a stagnant fluid, when there's no movement inside the fluid, H is low. When H is low, then the resistance by convection is large. So in that case, this is the best case that I can use this long capacitor method for that particular case. So if this is the case, then we can say bio number is much smaller than 1 because the conduction resistance is much smaller than convection. Again, consider the example of the copper sphere inside air, which is not moving, right? Resistance by convection is large, resistance by conduction is really low. So bio number should be much smaller than 1. Which means that if I'm going to show such a case in this wall, then if temperature suddenly change on one wall, because bio numbers is small, then the temperature changes inside the solid object is small. So suddenly almost, if you go to the right hand side, no various changes. So about the same TS might equal TS2. So this is TS2. And then of course you have heat loss by convection. Now consider this with the case that Bayo number is very large, much greater than 1, for example 10. And what that means that resistance by conduction is much larger than resistance by convection. Example of this can be if you have a plastic object you're putting in a liquid. So the resistance by conduction is high because K of the plastic is low. So overall LC over Ka resistance by conduction is high. And the resistance by convection is low, you have liquid. So there's a huge temperature difference between going from one side of the plastic object in this case, to the other side. So TS2 in this case, there's a huge temperature difference across the object itself. And then of course you have heat loss by convection. So this is a case for Bayo very large. Now for Bayo around the 1, you can have almost this form. So this is Bayo about 1. So in this course, we are only can use long capacitance method when Bayo number is less than 0.1. So this is the condition we have to check. So we always have to check if for the particular example we're trying to solve, Bayo number is less than 0.1 or not. We have to show it first of all, yes, it is less than 0.1, and then go ahead, use the star equation, long capacitance method equation. If bias is greater than 0.1, then we cannot use this approach. Now, let's go to the next slide. I'm going to define another new variable, Fourier number, and that's about it. And then we're going to solve an example. Almost done. So let's move on to the next slide. We're going to talk about a Fourier number. So first of all, let me define Fourier number. We show Fourier number FO as alpha, thermal diffusivity, times T time over characteristic length to the power of 2LC squared. This is Fourier number, dimensionless Fourier number. Now, to show that how it comes inside the long capacitance method equation, remember we showed theta over theta I, or T minus T infinity divided by Ti minus T infinity, equal to Ti minus T infinity equal to e to the power of a constant, which was h as over rho Vc times T, okay? Now what I'm gonna do right now, I'm gonna work with this one a little bit. Say we have h as T over rho V Cp. By the way, this is Cp. Okay, so I can go ahead and say, can I show it with H, T, and on denominator, I would like to have rho Cp, and instead of area divided by volume, I'm gonna put L sub C, characteristic length. Remember, characteristic length was V over area. Is this correct? So H times T divided by rho Cp, instead of As over V, I have 1 over LC. And now, what I'm gonna do, I'm gonna say, okay, can I make HLC over K, HLC over K, then I added the LC here, I added the K here, and times K over rho C times T over LC, and it should be a square. Why a square? Because I added one LC here, so one LC should cancel out the other one, and I have another L sub C here, so this becomes L sub C. So let's double check, make sure we are right. If I cancel out this one and this LC with one of the LC, I should have H times T, which I have, divided by rho CP times one LC. So this is correct. Uh-oh. So that was 2, this is this. So what I did, I added a few terms, variables, I removed it. So at the end, what is this? This is nothing but 1 over alpha, correct? Or this is alpha. Alpha, yes. So K, okay, so let's put it this way. This is, alpha is K over rho C. My bad. Sorry, this is exactly alpha. What is this? This is HLC over K. This is nothing but bio number, remember? Bio. So I can show that I have bio number times alpha T over LC squared, which kind of created a Fourier number. So I have bio times Fourier, which means that I can go ahead and rewrite my main lump capacitance equation, T over Ti, theta over theta I equal to T minus T infinity, Ti minus T infinity equal to E to the power of minus, instead of HAS rho VCP, I can go ahead and say bio times Fourier. So that's it. That was another form of showing this. I'll make sure I covered this important form. Now let's review. Feel free to pause the video, review what you have learned so far. We're gonna do one example here, and I'll share more questions as an additional example later. So let's do this example first. I have another example ready. If you need to, we're going to cover that as well, but both of them are about the same. So as long as you know, you understand the equation, you can really simply use it. So let's do one quick example. Example 1. We have a spherical aluminum, with a weight of 6 kilograms and initial temperature of 300 degrees C, very, very hot, is suddenly immersed in a fluid at 20 degrees C. The convection heat transfer coefficient is inside the fluid. H is 58, watt per meter square Kelvin. Remember, you have to know the units of H, units of K, units of alpha. Now the question is, estimate the time required to cool the aluminum sphere to 90 degrees C. So initially it was 300. We're gonna find out how long it will take to go from 300 all the way down to 90 degrees C. And using long capacitance method, okay? So this is what we have. There's a liquid is at 20 degrees C, and also H is known as well, 58 watt per meter square Kelvin. Object initially at 300 degrees C, drop it into the water, and you want to find out how long it takes this to go to 90 degrees C. Well, the properties of the material should be given to you, otherwise you should be able to have it from the table at the end of the textbook. Let me go ahead and summarize the information we have. Mass is 6 kilograms, mass of the object. Ti, initial temperature of the object, is 300 degrees C. T infinity, which is the fluid temperature, is 20 degrees C. H is given 58. T, or the final temperature, is given. That's what we have, 90 degrees C, the final temperature of the object. In rho, the density of the object, it should be given to you. Let's say rho of the aluminum sphere is 2,702. Unit of rho is kilogram per meter cubed. By the way, you should be able to find it from table A1. Okay. C is given, so for liquid, for solid and liquid, Cp is equal to C. We don't have control volumes or a specific capacity at control volume. So at fixed volume. So the constant volume is a constant pressure. We have in the thermodynamics, but not in really incompressible fluids. So C is 903 unit of C, joule per kilogram Kelvin or kilogram degree C. You can still find it from table A1. And also thermal conductivity of the object is 237 watt per meter Kelvin. So to solve this, first of all, this is the main equation we're going to use. T minus T infinity divided by Ti minus T infinity equal to e to the power of minus h as over rho CV or C times V volume, and all of it times time. So all of it times time. So in this problem right now, we know final temperature 90, we know T infinity 20 degrees C, initial temperature we know, H we know, AS we can find that, rho we know, C we know, volume we can find that. We're looking for how long it will take to go to 90 degrees C. So we're looking for T, time. So what is the volume of the object from the information we have? We have the mass, we have the density. So volume is mass over density. So 6 divided by 2702 gives us 2.22 times 10 to negative 3 and meter cubed. We're also looking for surface area, correct? So once we have the volume, I can go ahead for a sphere. Volume is 4 over 3 pi r cubed, which is equal to 2.22. So radius of the sphere, you can find it as 0.0809 meter. Now, once I have the radius, I can go ahead and find the surface area for a sphere. Area is 4 pi r squared, which if you use this radius we found, times a squared times 4 then pi, your surface area would be 0.0822 meters square. Now, can we use long capacitor method at all or not? To find the answer, we have to calculate the bio number, see if that's less than 0.1 or not. So for bio number, we need LC, right? So LC, we said this LC is equal to V over A. I have the V, I have the A. So in my case, V over A would be 0.02696, and we can show that this is less than 0.1. So yes, we can go ahead and use it. So in homework, in exam, in quizzes, I want you to show the check process and make sure. Oh, sorry, this is LC. We still should go ahead and calculate the bio number. My bad. So once I have LC, I can put it here. Hopefully, bio number is less than 0.1. Bio is H LC over K. And in this case, H is 58. LC is this tiny number. And K is 237. So this is bio, which is 7.66 times 10 to negative 3. Now, because it's less than 0.1, this is the check. You can go ahead and use this approach. So because bio number is less than 0.1. Now that I check the bio number is less than 0.1, again, I want you to show this check process. Otherwise, there's a grade associated just for this bio check that you're gonna lose it if you don't show it. Then I'm gonna substitute everything in this main equation, find the time. So again, I had t minus t infinity, ti minus t infinity, e to the power of minus has over rho v c times t. Now, if I'm gonna substitute the numerical values, t is 90, t infinity was 20, initial temperature was 300, t infinity is 20, e to the power of minus, h was 58, times surface area, we found it as 0.0822, density was 2702, C was 903, volume is 2.22 times 10 to negative 3, and times T. Left-hand side becomes 0.25 equal to e to the power of minus 8.87 times 10 to negative 4 times t. If you solve this, it gives you t is equal to, if you take ln from both sides, you have natural log of 0.25, and ln of e to the power of something is basically whatever inside the parentheses, minus 8.87 times 10 to negative 4. So your time would be 1,563. By the way, the unit for time should be second. Now you can convert it, say this is around 26 or half an hour, 26 minutes. So make sure you can handle this section, that once you have it in this form, in order to go to this section, you want to take ln, natural log from both sides. What happens is ln of e to the power of x is equal to x, right? Ln of e to the power of this is becomes whatever we had inside, so the rest of it was easy. And this is the power. So this is the example. I have another example. What I'm going to do, I'm going to scan it and email it to everyone. One last point here and we'll be done. On LC, we define characteristic length as volume divided by area. For simple shape, it's easy, right? You find the volume, you find the area, you divide volume by area. Now, LC for sphere, for cylinder, and for walls is estimated in the textbook. You don't need to go through V over A. You can simply say LC for a sphere is equal to, let me make sure, is equal to radius divided by 3. For cylinder, you can say, for long cylinder, as it say, from the textbook, LC is equal to radius over 2. For walls with a thickness of 2L, thickness of 2L, then LC would be simply L. So if this is a wall, thickness of 2L, LC is L. So this is, so either way is fine. If you're gonna go with a conservative approach, as textbook says, calculate volume, calculate area, this is surface area, of course, and divide it together and find LC that's accurate, that's perfect. Otherwise, feel free to use these relation. If you know the radius of the sphere, LC, you can feel free to use it R over 3, R over 2 for cylinder, half of the thickness of the wall as well. That's it. Thank you so much for listening. Make sure you go back, you emphasize on areas that perhaps more important, or you have more questions. Feel free to read the textbook or contact me if you have any questions. Definitely meet in class and go over this if there's any question. I'm going to send you an example on this and a homework on this. And this is the end of chapter 5. So we covered transient conduction, but make sure if a problem to be solved in transient conduction, first of all, you want to show that the bio number is less than 0.1. So that check process is important. You have to show it. Then use the equation we talked here to find either if temperature, final temperature is known, to find time, or if you want to find out after 200 seconds, what would be the temperature, you can find T. Another point is that If problem statement says after 26 minutes, you have to convert that minute to how many seconds and then use the t. You can't use minute or hour or days in t, just one unit of second, the way it develops. That's it. That's transient conduction. That's a nice approach for transient conduction. I don't think we cover more than this in terms of transient conduction in this course. That's it. Thank you so much for watching this video, and talk to you soon.